Now let us see about aromaticity. What is aromaticity? Aromaticity is a state of stability that any molecule would try to achieve. Aromatic molecules are cyclic, planar, and have 4n plus 2 pi electrons, which are continuously delocalized in a cyclic manner. According to Huckel's rule, organic compounds can be classified into aromatic compounds, anti-aromatic compounds, aliphatic or non-aromatic compounds. What are aromatic compounds according to Huckel's rule? According to Huckel's rule, a molecule should be planar, cyclic, and they should have 4n plus 2 pi electrons, and the pi electron should be continuously delocalized. The pi electrons may be with or without lone pairs, negative charge or positive charge. And the number of pi electrons should be 2 pi electrons or 6 pi electrons or 10 pi electrons or 14 pi electrons and so on. And all the aromatic molecules are said to be more stable. Hence, according to Huckel, the molecule which is cyclic, planar and have 4n plus 2 pi electrons and the pi electrons are continuously delocalized in the molecule, then the molecule is called as aromatic, and aromatic compounds are more stable. According to Huckel, what is anti-aromatic compound? Anti-aromatic compounds are cyclic, planar, but they will have 4n pi electrons which are continuously delocalized. And all the anti-aromatic compounds are unstable in nature. The only difference between aromatic and anti-aromatic compound is aromatic compound will have 4n plus 2 pi electrons and anti-aromatic compounds will have 4n pi electrons. Both aromatic and anti-aromatic molecules are cyclic, planar in nature, and the pi electrons will be continuously delocalized within the molecule, but the only difference is aromatic compounds will have 4n plus 2 pi electrons, whereas anti-aromatic compound will have 4n pi electrons. And all the aromatic compounds are stable and all the anti-aromatic compounds are unstable. And all the molecules preferred to be aromatic. And what is non-aromatic or aliphatic compounds according to Huckel? If a molecule is cyclic or not cyclic, it may be planar or non-planar. It may have 4n pi electrons or 4n plus 2 pi electrons, but there is no delocalization of pi electrons. All the pi electrons are localized between two carbon as pi bonds and they will not get delocalized. If there is no delocalization of pi electrons means, then that compounds are called as non-aromatic or aliphatic. Hence, the only difference between aliphatic or non-aromatic compounds and aromatic anti-aromatic compounds are aromatic and anti-aromatic compound will have pi electron delocalization, whereas non-aromatic compound will not have delocalization of pi electrons. Coming to the order of stability, aromatic compounds are more stable, then comes non-aromatic or aliphatic compounds, and anti-aromatic compound is least stable. Coming to 3-membered cyclic species, let us take cyclopropene, 3 carbon containing ring with 1 double bond. Cyclopropene. Cyclopropene seems to be cyclic. It is having a ring structure. It is planar, that is 3 carbon atoms and all the hydrogen atoms are lies in a same plane or single plane. There is only 1 pi bond which contains 2 pi electrons and there is no delocalization. Hence, the compound is non-aromatic according to Huckel. Coming to cyclopropenyl cation, it has resonance structure. Cyclopropyl cation is cyclic, planar. It has 2 pi electrons and also a positive charge. Therefore, there is a continuous delocalization of pi electrons between 3 carbon atoms. Therefore, the molecule is aromatic and more stable. Coming to anion, anion is also cyclic, planar, but it has 4 pi electrons and continuous delocalization and falls under the category of anti-aromatic and unstable. So, comparing cyclopropene, cyclopropenyl cation and cyclopropenyl anion, cyclopropenyl cation is aromatic and more stable and it is a preferred conformation, whereas cyclopropenyl anion is anti-aromatic and unstable, and cyclopropene acetus is non-aromatic. All the three are cyclic. All the three are cyclic in nature. All the three are planar in nature. And cyclopropene has 2 pi electrons. Cyclopropenyl cation has 2 pi electrons and positive charge. Cyclopropenyl anion has 2 pi electrons and a negative charge, total 4 pi electrons. Whereas cyclopropene, there is no delocalization, hence it is non-aromatic. Whereas cyclopropenyl cation, it falls under the category of aromatic Huckel's rule. It obeys 4n plus 2 pi electrons, therefore it is aromatic and more stable. Whereas anion falls under the category of anti-aromatic, that is 4n pi electron, and it is anti-aromatic and unstable. Therefore, in 3-membered species, cyclopropenyl cation is more stable and aromatic. Coming to 4-membered cyclic species, let us take cyclobutadiene or 4-annuline. 4 carbon containing ring with 2 double bonds, alternative single and double bonds. The molecule seems to be cyclic, planar, and it has 4 pi electrons. There is a conjugation, single bond, double bond, single bond, double bond. Hence, there will be a continuous delocalization of pi electrons. The pi bond or pi electron will not be localized between these 2 carbon and these 2 carbon. It will be delocalized between 4 carbon atoms. All the 4 pi electron will get delocalized, and there will be a continuous delocalization of pi electrons within the molecule. Therefore, it falls under the category of 4n pi electrons, which is non-anti-aromatic and unstable. So, as it is, cyclobutadiene is anti-aromatic and unstable. We cannot synthesize the cyclobutadiene in lab, but it can be isolated under controlled conditions such as in organ matrix or using trapping agents such as dienes. So, in this reaction, we can isolate cyclobutadiene. Since it is anti-aromatic, we cannot synthesize, but we can isolate by using trapping agents, cyclopentadiene, that is by using Diels-Alder reaction and forming a Diels-Alder adduct, we can trap this cyclobutadiene, or we can dimerize this cyclobutadiene. Hence, we can isolate this cyclobutadiene. It is anti-aromatic and unstable, so we cannot synthesize it. Coming to cyclobutadienyl cation, the molecule is planar, cyclic. It has 2 pi electrons and positive charge, and therefore there is a continuous delocalization of pi electrons, and it falls under the category of 4n plus 2 pi electron, that is aromatic system. Therefore, it is aromatic and more stable. See, here ionization of 3,4 dichloro and 1,2,3,4 tetramethyl cyclobutene will take place, and it forms dication. This reaction is possible because the formed ion is more stable because it acquires the aromatic character. Therefore, the ion formation is easy here, and it is attributed to the formation of aromatic character and stability. So, hence in 4-membered cyclic species, that is cyclobutadiene, as it is anti-aromatic and unstable, whereas cyclobutadienyl cation is aromatic and more stable. Therefore, it is preferred conformation for 4-membered cyclic species, that is cyclobutadiene. So, cyclobutadiene prefers to be cation. Coming to 5-membered cyclic species, cyclopentadiene. Cyclopentadiene, as it is cyclic, planar. It has 2 pi bonds, therefore 4 pi electrons, but there is no conjugation, single, double, single, no conjugation. Therefore, no delocalization is possible, and the pi electrons will be localized between these 2 carbon, and this pi electrons will be localized between these 2 carbon. There is no delocalization. Therefore, it is non-aromatic. And coming to cyclopentadienyl cation, the molecule is cyclic, planar. It has 4 pi electrons and a positive charge. Therefore, delocalization will be possible, and here it comes under the category of anti-aromatic compound, that is, it follows 4n pi electron rule, and it is unstable in nature. Coming to cyclopentadienyl anion, this molecule is also cyclic, planar, but it has 6 pi electrons, that is 4 pi electrons plus negative charge, and delocalization is possible here. It follows 4n plus 2 pi electron rule and aromatic, more stable, and it is the preferred orientation. So coming to cyclopentadiene, all it's diene, cation and anion, all the three are cyclic in nature, planar in nature. It has 4 pi electrons. It has 4 pi electrons plus positive charge. It has 4 pi electrons plus negative charge. Whereas cyclopentadiene is non-aromatic. Its cation form is anti-aromatic and unstable. Its anion form is aromatic and more stable. Therefore, it is the preferred orientation for cyclopentadiene. So, cyclopentadiene exists as anion. It avoids to exist as cation. And why cyclopentadiene is acidic? It is the same reason. If it loses H plus ion, it will form anion to acquire aromatic character and stability, which is the preferred orientation of cyclopentadiene. Therefore, all the cyclopentadiene will be acidic in nature. It prefers to lose H plus ion and forms anion, which is more stable and aromatic. This is the reason for its acidity. Coming to 6-membered ring, everyone knows benzene, which is also called as 6-annuline. Benzene is aromatic because benzene is cyclic in nature, 6-membered ring. Planar, all the 6 carbon atom and hydrogen atom lies in a single plane or same plane. It has 6 pi electrons, that is 3 pi bonds and 6 pi electrons. There is conjugation, single, double, single, double, single, double. Therefore, all the 6 pi electrons will get delocalized. They will not be localized between carbon atom. They will get delocalized, and hence there is a delocalization of pi electrons. Therefore, it is aromatic and more stable. Now let us see about 7-membered cyclic species, that is cycloheptatriene, 7-membered carbon containing ring with 3 double bonds. See, it is cyclic in nature, planar, all the carbon atom will lie in single plane, and it has 6 pi electrons. But there is no conjugation, double, single, single, double, single, double, single, no conjugation. Hence, there is no delocalization possibility. And the pi bonds or pi electrons will fixed or localized between the fixed carbons, and it will not delocalize. Therefore, the compound is non-aromatic. Cycloheptatriene, as it is non-aromatic in nature. Coming to its anion form, it is also cyclic, planar, and there are 8 pi electrons. And there is a delocalization of electrons. Hence, it follows 4n pi rule, 4n pi electron rule, Huckel's rule. Therefore, it is anti-aromatic and unstable. Cycloheptatriene will never prefer to be in anion form. Coming to cation, tropylium ion, it is called as tropylium ion. Cycloheptatrienyl cation is called as tropylium ion. It is also cyclic, planar. There is 6 pi electrons and a positive charge. Therefore, delocalization is possible. Hence, it is aromatic and more stable since it follow 4n plus 2 pi electron, Huckel's rule. Therefore, it is aromatic and more stable. It is the preferred orientation. Therefore, cycloheptatriene prefers to be tropylium ion, cation, and not anion, because cation is aromatic and more stable. Anion is anti-aromatic and unstable. There is one interesting concept here. All the alkyl halides such as cyclopentyl chloride are non-polar and dissolve in non-polar solvents and remains insoluble in water. Surprisingly, the cycloheptatrienyl bromide is an exception. It is insoluble in non-polar solvents but dissolves in water. Why? Because the concept behind is aromaticity. If it is in ionic form, that is tropylium ion, if it is in ionic form, Br minus and tropylium ion, that is cycloheptatrienyl cation, it acquires aromatic character and it is more stable, which is the preferred orientation for cycloheptatrienyl triene. Therefore, it dissolves in water. It dissolves in water. It is an ionic compound, and it acquires aromaticity because of the formation of tropylium cation, which is a stable conformation or preferred orientation. Therefore, it is the reason for its dissolution in water. And why cycloheptatriene is less acidic than cyclopentadiene? It is the same reason that if it loses H plus ion, it forms anion. Anion is anti-aromatic, therefore it does not prefer to lose H plus ion, therefore its acidity is low. Its acidity is low. Whereas cyclopentadiene as it is anti-aromatic, And if it donates a proton if it loses a proton, it becomes more stable and it acquires aromatic character, therefore it is more acidic. Therefore, cycloheptatriene is less acidic than cyclopentadiene. The concept behind the acidic nature is aromaticity. Coming to 8-membered ring, that is cyclooctatetraene, which is also called as 8-annuline. 8 carbon atoms with 4 double bonds. The compound seems to be cyclic. If it is planar, it will have angle strain. It has 8 pi electrons. There is conjugation, alternative single and double bonds. Therefore, delocalization is possible. But it follows 4 n pi electron. That is the Huckel's anti-aromatic rule. Therefore, the compound is anti-aromatic and unstable. Since it has angle strain, it does not prefer to be planar. Immediately, it changes its structure to tub-shaped or boat-shaped. If it comes to boat-shaped or tub-shaped, still it is cyclic in nature only. It is a ring form only, but it is not planar. See, these 2 carbon atoms and these 2 carbon atoms, totally 4 carbon atoms will be in one plane, and this 4 carbon atoms will be in another plane. Therefore, the electrons cannot move in 2 planes. Delocalization is not possible. Even though it has 8 pi electrons, there is no delocalization. Therefore, it is non-aromatic. It prefers to be non-aromatic because there occurs stability. So, as it is anti-aromatic. If it loses its planarity and comes to tub shape or boat shape, it is non-aromatic, and it is a preferred orientation for cyclooctatetraene or 8-annuline. Coming to cyclodecapentylene, that is 10 pi electrons, 10 carbon atom containing ring and 5 double bonds. If we see this structure, definitely it will have angle strain. Therefore, the planarity is not possibility for this ring. Immediately it changes its structure like this. Here, puckered form, it is called as puckered form. But in this puckered form also, planarity is not there because these 2 hydrogen will have steric effect or steric interaction will be there. Therefore, the planarity of the molecule is not there. The molecule loses its planarity to avoid the interaction between the inner hydrogens. That is the hydrogen present in carbon 1 and 6. There is an interaction between these 2 hydrogens. Therefore, to avoid this interaction, the molecule loses its planarity. But we can make it aromatic by bridging 1 and 6 carbon, or by directly connecting 1 and 6 carbon, converting it into naphthalene. We can acquire aromaticity. So coming to aromaticity in annulenes, already we have seen 4 annuline, 6 annuline, 8 annuline and 10 annuline. Now let us see about 12 annuline. 12 annuline it has 12 carbons with 12 pi electrons, and according to Huckel, it is anti-aromatic and hence it is not stable above -50. But its dianion, which has 14 pi electrons according to Huckel, it follows Huckel's rule, 4n plus 2 pi electrons rule. Therefore, it is aromatic. So, 12 annuline, if it is dianion, it is aromatic. But as it is anti-aromatic and unstable. Coming to 14 annuline, it obeys Huckel's rule, but there is an interaction between the inner hydrogen atoms. Therefore, it is weakly aromatic in nature. The inner hydrogen atom, chemical shift of inner hydrogen atom will not comes under the value of 6 to 8, whereas the outer hydrogen atoms will comes under the value of 6 to 8 delta value chemical shift. Therefore, it is called as weakly aromatic. 14 annuline is weakly aromatic. It does not bear the hallmark aromatic property of chemical stability, and hence it quickly decomposes when exposed to light and air. But we can make it aromatic by converting one double bond into triple bond, or by bridging the 4 carbons 3, 6, 10, 13. By bridging the 4 carbon atoms, we can make it aromatic, completely aromatic or fully aromatic. Coming to 16 annuline. 16 annuline, its dianion shows aromatic character. And because of the vast structure, it shows a polyene characters. It shows polyene character because it is non-planar and non-aromatic. Coming to 18 annuline. 18 aniline is completely aromatic and 100% aromatic because the inner there is enough room internally to accommodate all the hydrogen atoms without significant distortion of bond angles. And the cavity within the 18 aniline is sufficiently large, and hence the steric interaction involving inner hydrogen is minimum. There is a minimum steric interaction between the inner hydrogens, and hence the inner hydrogen will not shows a NMR chemical shift value around 6 to 8, and the outer hydrogen shows the NMR chemical shift value around 6 to 8. And 18 aniline is completely aromatic. We can even remove all the hydrogens and bridge the carbon atoms to get complete aromaticity. Coming to fused polynuclear hydrocarbons, comparing naphthalene and anthracene, both are cyclic, both are planar. It has 10 pi electrons, anthracene has 14 pi electrons and obeys Haeckel's rule, 4n plus 2 pi electron rule. Both have conjugation, both have delocalization of pi electrons, both are aromatic and more stable. Now let us see about azulenes, pentalenes and heptalenes. They are non-benzenoid compounds. And azulene shows significant aromatic stabilization and have noticeable dipole moment. What is the reason for it? It is a combination of cyclopentadienyl anion and cycloheptatrienyl cation. See here, it is a combination of cyclopentadienyl anion and cycloheptatrienyl cation. It is this ring is aromatic and this ring is also aromatic. It is a combination of two aromatic rings, cyclopentadienyl anion and cycloheptatrienyl cation, that is tropylium ion. Both are aromatic individually. Therefore, azulene is a combination of two aromatic rings. Whereas pentalene is not aromatic and heptalene is also not aromatic. They exist. They are not stable. They are not stable and they are anti-aromatic in nature. Coming to fulvalene. Fulvalene represents an interesting class of compounds with the potential aromaticity. But this pentafulvalene and heptafulvalene, they exhibit only poly in character and does not show any aromatic character. But combination of cyclopentadiene and cyclopropene, if we examine that, they have dipolar resonance structure because of the concept of aromaticity that exists within the molecule. See, coming to this combination, cyclopentadiene and cyclopropenyl are ringed. If we consider this type, if we shift the double bond here, the ring will have negative charge and this ring will have positive charge. If we shift this double bond like this, then the 3-membered ring will have a negative charge and 5-membered ring will have positive charge. Let us analyze separately. Here it is cyclopentadienyl anion, which is aromatic in nature. It obeys Haeckel's rule. Similarly, cyclopropenyl cation, it is aromatic in nature. It obeys Haeckel's rule. Therefore, this ring, this fulvalene, which exhibit dipole moment, is a combination of two aromatic rings. Whereas here it is anti-aromatic and this ring is also anti-aromatic. It is a combination of two anti-aromatic rings or non-aromatic rings. Therefore, the fulvalene prefers to be in this form only. Coming to signones. What is signones or syndones? Syndones or signones are mesoionic heterocyclic chemical compounds possessing 1,2,3 oxadiazole core with a keto group in position 5. It is dipolar. It possesses both positive charge and negative charge. Number 1, according to Haeckel's rule, it is aromatic since the molecule is planar and it contains 4n plus 2 pi system. Therefore, the molecule is said to be aromatic in nature. But later, computational studies shows that it is not aromatic in nature. It is non-aromatic. In 1998, Simas et al. Performed computational calculations, and they come to conclusion that this signones has two separate regions of charge or two separate regions of delocalization. There is not one complete delocalization, and the electrons are delocalized over regions separated by a single bond here, N carbon, oxygen carbon. Therefore, there is a two separate charged regions or delocalized regions. Therefore, it is non-aromatic. They come to the conclusion that Simers et al. Come to the conclusion that they are not aromatic because it does not have complete delocalization. The delocalization, there is a two part of delocalization which is separated by a single bond. And in Gilchrist's book, that is heterocyclic chemistry, they also mention that mesoionic compounds are that is classify signones and other it does not therefore seem useful or appropriate to classify signones and other mesoionic compounds as aromatic. That is, they also supports that signones are not aromatic in nature. In this book they said that signones are not aromatic in nature. But later in 2013, Paul Schleyer et al. Put same computational calculations, but they measure Nix value. What is meant by Nix? Negative nucleus independent chemical ship value. And they compare this Nix value of benzene, pyrrole, furan with signones and machnones. They observed that all the Nix values are similar to benzene. Therefore, signones should be aromatic, which is similar to benzene. They conclude that Paul Schleyer et al. They conclude that signones and machnones are aromatic in nature. So these are the riddle that surrounds signones. First come Huckel's rule. According to Huckel's rule, signones should be aromatic. But later Simers et al. Said that signones are non-aromatic in nature because there are two separate delocalized regions which are separated by single bonds. Gilchrist's books on heterocyclic compound also support that signones are not aromatic. But later Paul Schleyer et al. Concludes that signones are aromatic in nature by computationally calculating the Nix value, that is negative nucleus independent chemical ship values, and they found that the value is comparable with that of benzene, and hence signones are also aromatic in nature. Coming to tropalones. Tropalone shows aromatic character. It resists hydrogenation, it undergoes diazo coupling and can be nitrated, sulfonated and halogenated, that is, they show electrophilic substitution reactions. And what is the reason behind it is aromaticity or concept of aromaticity and existence of dipolar structure. See here, this is tropalone, but it exists in dipolar structure, that is ring with positive charge and O with negative charge. 7-membered ring containing 3 double bonds and a positive charge is called as tropylium ion, which is more stable in nature, and it obeys Huckel's rule of aromaticity 4n plus 2 pi electron rule, cyclic planar, complete delocalization, 4n plus 2 pi electrons are present in it, and it is called as tropylium ion, which is said to be more aromatic and more stable. Therefore, tropalones exist as dipolar structure and are also have aromatic character. Thank you.